All right, so let's look at an application problem. This is a very common application problem you look at with quadratics. Anytime you're dealing with projectile motion, an object will go up and then, force of gravity brings it back down. It kind of follows the pattern of a parabola. And so we're going to look at that here as an archer's arrow follows a parabolic path. The height of the arrow can be modeled by this equation here, where x is the arrow's horizontal distance in feet. All right, so A asks, what's the maximum height of the arrow and how far from its release does this occur? Okay, so to find the maximum height, you kind of, when you're doing these application problems, you have two types of problems that you'll be looking at. Or am I doing like a maximizing, minimizing type of problem? Or am I finding when an object hits the ground? Or am I finding a zero? Or is it, which I call a solving problem? So am I doing a solving problem or a maximizing problem? Okay, in this case, I'm doing a maximizing problem. And so the key is on a maximizing problem, the first thing you want to do is you want to find the x that the graph is maximized. So how do you find the x that the graph is maximized? You do the axis of symmetry formula. X equals negative b divided by 2a. Okay, and so we can go up here and identify that a is the coefficient of the x squared. B is the coefficient of x, and so we plug those into this formula, okay? So this is what you use when you're doing a maximizing problem or minimizing problem. So maximize, minimize, you're using that formula there, okay? So x equals negative b, so negative 2 divided by 2a, 2 times negative 0.005. And so we can find those values. Negative 2 divided by, whoops, didn't mean to do cosine. 2 times negative 0.005. So that'd be 200. Now, what does that mean? That is my x point where it's maximized. X is the horizontal distance in feet. So that tells me how far the arrow will travel horizontally, so like left to right, before it hits its maximum point. But we actually want to know what the maximum height is. So to find the maximum height, we've got to plug in 200 into our function. So I'm going to plug in 200 in our function. So I'm getting that 200 from there equals negative 0.005 times 200 squared plus 2 times 200 plus 5. Okay, and we'll figure out what that is. 0.005 times 200, I'll put parentheses around it, not that it matters in this case, squared plus 2 times 200 plus 5, and so you get 205. Did I do that correctly there? Okay. Think something, all right, here we go. So it's going to be 205 will be our maximum height. Okay. So next thing I'm going to do is I'm going to go ahead and find, I'm going to go to the next part and find the horizontal distance it travels before it hits the ground. Okay. And by the way, how far, I should clarify, how far from its release does this occur? Well, actually it occurs 200 feet is how far. And it's confusing because we've got both of these units are in feet. 200 feet is how far, that's I'm going to put horizontal distance. I'm sorry, both of my units are feet here. So this is not the best. And so this is the maximum height. All right. Next, find the horizontal distance it travels before it hits the ground. So when I'm looking for when it hits the ground, okay, if I'm visualizing when it hits the ground, I want to know when it hits the ground. Now, think about when you're on the ground, what's true? When I'm on the ground, anytime I'm on the ground right here, my y is equal to 0. Y and f of x are the same thing. So I want to know, I need to let f of x equal 0. This is what we call a solving problem. So you're going to plug in 0 for f of x. Negative 0.0005 x squared plus 2x plus 5. So this is what we call a solving problem, because what you're doing here is you've got an equation, you've got to equal to when it hits the ground equal to 0. So this is a solving problem. So how do you do a solving problem? Well, it's a quadratic equation. So we got to use one of those methods that we learned. Remember that I like quadratic formula because it always works. Okay, so I'm going to kind of, but you can try factoring. I don't think this is factorable, but I'm going to do a method that always works. So I'm going to do quadratic formula. So A is the coefficient of x squared, the number in front of x squared. B is the coefficient of x. C is the constant. And so I'm going to plug those into this formula. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, all I did was plug in numbers there. And remember, our next step is to simplify around the plus or minus. So I'm going to simplify around the plus or minus. So that's negative 2. 2 times negative 0.005. That's negative 0.01. Now, this time I'm going to do something a little different. I'm doing a real world scenario, so they want to know the round the nearest foot. So instead of keeping it in the simplest radical form where, you find what's underneath the radical, the discriminant, and then simplify it, I'm going to type in the square root because this time what I want to do is I want to figure out like an approximation in terms of, instead of a radical form, just give a more of a numerical estimate because that would be, a better estimate for the person that's using this. So I'm going to go 3 spots, 2.025. Okay, and then now I've got a plus or minus, so I'm going to write 2 separate equations. Negative 2 minus 2.025 divided by negative 0.01 and negative 2 plus, I don't know why I did them in that order. All right, and we're going to figure out what these are. So, and I'm going to put the top in parentheses, negative 2 minus 2.025 divided by negative 0.01. So I got 402.5 here. And I guess that would be feet. And then negative 2 plus. So I'll change this one to a plus. Ooh, negative 2.5 feet. Now, let's think about in terms of what we're talking about before it hits the ground. And you're going to get 2 answers usually on a quadratic equation. And in this real world scenario, like a lot of them, not every one of them, but a lot of them like this, you're going to end up throwing out the negative because that's an extraneous solution because it wouldn't make sense to have negative feet. So 402.5 feet is how long it takes for it to hit the ground. Now what I'm going to do is I'm going to model this, and I'm going to use some things that I've gathered from this information to help me model this. First thing, there's something that I have not gathered from these two that I know from the original equation, and that's the y-intercept. So the y-intercept is just the constant, okay, in the equation. I call this standard form. This book does not call it standard form. I call this standard form. The y-intercept is just the constant. And so that's going to be 5, or I can put 0.5. Okay. Other things that I know, well, I know this maximum height, this point here, what I did in part A, that gives me the vertex. Okay, the vertex comes from there. The x for my vertex is 200. The y is 205. And so the vertex comes from there. Okay, so I have that point. And I also know when it hits the ground. Okay, so it hits the ground. Now that's technically an x-intercept at 402.5 and 0. Okay, so I've got 3 points to work with here, and I'm going to use those 3 points. So the y-intercept, now, before I do that, I need to make my graph here. I'm going to go by increments. I got to go up to, on the y, my highest y is 205. So why don't we go up to 300? I'm trying to think here. How many tick marks do I have? I'll go up to 250. So 50, I'm going to label every other one. 150, 200, 250. And this is the height of the arrow. Height of arrow. That's f of x. So this is your f of x right here. And then your x over here is your horizontal distance. I wrote that too close because I'm going to need to put numbers there. The horizontal distance and so my highest one's 402.5, so I need to go to at least that. I'm gonna go to let's kind of do this. Well, I'm gonna go by 50s here. 300, 400, 500. Okay. So I'm going to plot the y-intercept, which is 0, 5. So 0, 5 is down here. Okay. The vertex is 200 and 205. By the way, that y-intercept, you could also, it's the height basically that's the height that it's released from. So like whenever the person might be, you're releasing the arrow a little bit underneath like your true height. So they're releasing it 5 feet from the ground and it goes up. It comes back down at 402.5. And so it would look like this. And you're going to kind of round it there. And then it comes back down like that. There's a sketch of the graph. And let me try that a little bit better there. So this would come down and then hit there. All right. So there's your sketch of the graph for the arrows parabolic